as you want.
We prefer to start. Maybe we can have more extra time at the end.
For
Maybe for
questions,
sure.
okay.
Yes, for sure. We'll have too much people. They want to ask some questions for sure. Especially
Okay.
when we talk about the battery, and
Yeah.
especially when we have the battery on charge or battery on health. So for sure, now we have a new term SOF. For sure, today is very interesting talk for sure. Really, our chapter as chair, I thank everybody to be here. And first, we have to thank Dr. Mo Yang Cho for this opportunity to have a special lecture for the smart battery. We really appreciate you, Dr. Cho. And we can start right now. Dr. Shu, in his degree in electrical and computer engineering, computer communication, and now we are working with smart battery from the University of Wisconsin-Madison, NBS, in 1982, and from Cornell University in 1983 as master, and for sure his PhD in 1987 in same university, Cornell University. The professor or Dr. Shu is a professor in the Department of Electrical and Computer Engineering at North Carolina State University, and he was a visiting professor at Shangjian Scholar. So I don't pronounce it very well, but it's going well. Dr. Shu is a founding director of the Advanced Diagnosis, Automation, and Control Laboratory. He is a founding chair of Industrial Electronics Society, so IES, for Energy Storage Technical Committee, and the past chair of IES Resilience and Security for Industrial Application Technical Committee. Dr. Shu has published more than 350 articles, and he is holding 8 patents relating to his research work. Dr. Shu recent, Dr. Shu's recent research focus on distributed control and management on a smart grid, batteries, and mechatronic systems. He is an IEEE fellow, co-editor-in-chief of the IEEE transaction on industrial electronics, informatics, sorry, in 2014 till 2018. He is the editor-in-chief of the IEEE transaction on industrial electronics 2010-2012. He has received many awards, and the first one, it was from IEEE IES Dr. Engineer Agile Multi-Man Achievements Award, the IEEE Industrial Electronics Society Anthony Horfact Service Award, the IEEE Region 8 Joseph Biden Bash Outstanding Engineering Educator Award, and he is today a distinguished lecturer of the IEEE Industrial Electronic Society. Dr. Shaw has many research, and especially today, he will give a very nice, I suppose, and I'm sure, the webinar entitled Smart Battery Coach and SOC, SOH, SOF, and for sure, he will explain all of them today in terms of estimation. So, Dr. Shaw, the floor is yours, and again, we are proud to have you, and thank you very much for your time.
Thank you very much, Dr. Kassan. And I will share my screen. Make sure that let me see. Share home. Okay. Let me try again and share a window. And this is here. Okay. Can you see my screen?
Yes, it's fine.
Great, thank you. Let me set it up properly. Okay. Yeah, thank you very much, Dr. Hossein and Dr. Arnold. And I apologize if I pronounce your name a little bit
It's
wrong.
fine. It's fine, dear professor. It's fine.
Okay, thank you. And thank you to the Lebanon chapters for arranging this distinguished lecture and also for all your attendance. It's my pleasure here to share our work in batteries with you. Today, the topic is the smart battery gauge and state of charge, state of health, and state of function estimation. Our will be a 30 minutes presentation and 15 minutes Q&A. Now, in this presentation, and we will first give a brief description of IES because this is a IES distinguished lecturer. And also I will give some basic of batteries and then talk about state of charge, state of health, and state of function co-estimation algorithm that our lab has been developing in the last 15 years. And we will do some demonstration of the smart battery gauge and on the grid and also on an electric vehicle. And then we have a Q&A section. So since this is a 30 minutes presentation, I will give a very high level presentation on the subject. We will put some of the related publications in the slides for you. If you have any questions, please do not hesitate to contact me. So before we go into the technical part of the seminar, I would like to use several minutes to briefly describe the IES to you. Many of you are already active in the IES and like your Lebanon chapters that we are very grateful for that. And also you have taken a leadership role and hope that we will see you all much more in the IES activities. For those who do not know much about IES, I hope that you will be interested in joining IES and get involved in the society. So the IES, through its members, encompass a diverse range of technical activities devoted to the applications of electronics and electrical science for the enhancement of industrial and manufacturing process. These technical activities address the latest development in intelligent and computer control system, robotics, factory, communication and automation, flexible manufacturing, data acquisition and signal processing, vision system, and power electronics. So the society continue to update its program of technical activity to meet the needs for modern industry. So you can see the homepage of IES in the link shown on the slide. So IES has 24 technical committees, and you can find more information from this website. So they have all those current chair of the technical committee and also their webpage link. If you are interested in some of the technical committee, just send an email to the technical committee chair to add you as a member. And also I have put the webpage of the IES in here and all those individual link here. So please go through them and hope that you will join some of the technical committee. Also, there are 5 major conferences in IES. The first one is the IECon, and then the ISIE, ICIT, and those 3 are major conferences. And then also we have other conferences. A major one also is INDI and ETFA. So you can find all those conference location each year, and then the time of submission and all those information from this IEEE conference link. And we have actually 3 major publications, and then we have in the last 2 years have recently established another 3 publications. So, and all those informations you can find it in the publication tab of the IES conference site. So the 3 major ones that we have quite a while, more than like 20 years or more, is like IEEE transaction on industrial electronics with impact factor 8.2, and the IEEE transaction on industrial informatics and 10.2, and industrial electronic magazine is a 6.6. As I mentioned, then we have recently also established several other transactions, open access transaction, and also we have several joint publications with other IEEE sister society. So again, I will highly encourage you, if you have not done so, that consider to join IEEE and IES. And those are the corresponding links. You can just hit it and then you can get there with much more detailed instructions how to do so. And you have any questions, and feel free to contact me. And my email is CHOW, my last name, at ncsu.edu. Any question before I move on to the technical part?
No questions, Professor, but just to remind you for the student, it's not so expensive. It's like $5 per year for student.
Yeah.
So.
Yeah, this fund, I think that the IES people has talked about it. If you join IES, if you're IEEE student member, then IES is free, if I remember correctly. But of course, if you talk about I understand your concern. Yeah, please bring this up to the membership chair of IES, that they may see what they can do. This is an absolute good question, yes. Any other question before I move into the battery? Okay, so again, if any question, just let me know. And now we haven't introduced IES, so let's jump into the webinar. The first topic we talk about is about the basics of battery. So the safe operation of the battery is one of the most important things that an end user is concerned about. Like besides safe operation, we perform some survey with EV and large-scale battery users to identify what other factors are important to them. They are interested in knowing the appropriate operating condition, how fast to charge and discharge, what are the safety temperature range that the battery can operate in, how healthy is the battery, and when do we need to replace them. They also want the information in real time when the battery is in operation and without the need to use complex and computational intensive or labor intensive operations. So we can see that that is what the battery management system is doing, as what we will show in the next slide. So the battery management system, and we often call it BMS, are often used to perform basic battery management operations such as cell monitoring, health estimation, cell balancing, heat management, charge control, charge estimation, and battery safety. However, the current BMS has issues with inaccurate assessment of charge and health of the battery. As a result, there are issues with safety and protection, as what we talked about in the last slide. So we need to look closely on how to assess the charge, the health, and the functioning of the battery. So we have discussed many of those major issues in this paper list at the bottom of this wheel graph. And actually, we were grateful that this paper has been awarded as the best paper of the year in the IES magazine. So usually in the battery area, there are four major aspects of the BMS that we will be talking about today. The state of charge, we call it SOC, the state of health, which we call it SOH, the remaining useful life, we call it RUL, and the state of function, SOF. And the state of charge of the battery is defined in this equation is as the ratio of the charge left in the battery to the total charge of that the battery can hold. And the equation here represents the state of charge is I is the current being drawn or sent into the battery, T is the time, Q current is the capacity of the battery at its current state. The state of health is represented by two indices, the capacity and the internal resistance, which is shown in here. Now this is the equation is that Q nominal is the capacity of the battery when it was new, and Q current is the current capacity of the battery. The internal resistance of the battery is another matrix that commonly used to define the state of health. REOL is the resistance of the battery at the end of its life. our current is the current internal resistance of the battery, and our nominal is internal resistance of the battery when it is new. So the remaining useful life is the duration that the battery can be used before it needs to be replaced. So this is an important concept that is critical to end users. And also the state of function of the battery is defined as the ability of the battery to support a particular application based on its current operating condition, such as state of charge, state of health, temperature, etc. So those two indices are very application dependent. So in the later part of this presentation, we will share with you the driving range as an example for state of function calculation. So a quick description of how a lithium-ion battery works. So when the lithium-ion battery is using it, so we turn on the light bulb, and then we can play again, and then we can see that the lithium is going from the anode to the cathode, and then the electron is going through the users, and then they have a certain chemical reaction in here. Now, and then we go into the recharge mode, and then the lithium will reverse back from the cathode to the anode, and the chemistry is basically reversed. And then people commonly model this by a capacitor, which is QR, and then there's something called VOC, is open circuit voltage, and then VT is the terminal voltage across our applications, and then IL is the current. So we start to model this battery by using the circuits, and then you see that when the lithium is going from the anode and cathode, they will go through something called separator and going through all those materials, and we call internal resistance. So we model, so we have internal resistance on top of the previous model. And also, when the lithium, there's a different type of layer in here. So those the solvent inside. So when they go through it, there's a capacitance phenomenon or layer. So we call it double layer capacitance. Therefore, we add a R0 is that the DC level without all those dynamics into consideration, and then the resistance is that we consider the dynamics, and then the capacitance is also the dynamics when the lithium ion is moving from anode to cathode. And we have other battery that we have like a solid electric light interface, and then just add more system dynamics there. And so people call it diffusion effect. Based on this diffusion effect, we further modify or improve the accuracy of the electric circuit. So to add the ZW is a diffusion circuit. So by and large, so this represents different type of system dynamics of the battery. They have a short-term dynamics and long-term dynamics. Like for example, short-term dynamics is that we want to charge and discharge. We are talking about the legs like 1 minute to 10 minutes or 1 hour. Those are short-term dynamics. Long-term dynamics, like for example, like weeks to months to years. Those including like a self-discharge and different chemical behavior. So the diffusion effect, including the long-term effect and a stable voltage. So we end up is that this is one of the very common circuit model that people use when we do BMS. We have the self-discharge circuit in here. We have the voltage is on the anode side, and this is the Q is the how much the battery can hold the charge. And then they have a battery has a relationship with state of charge. And then the rest is that we have just previously present the R0, and then which is the DC resistance in here. And then the first short-term dynamics represented by this RC circuit. And then the long-term dynamics by this another RC circuit. Now the relationship between the open circuit voltage in here that we cannot directly measure, and with the SOC is also another measure that another state of charge we cannot directly measure, but that's why we need to estimate them. And we can directly measure the terminal voltage, and we can directly measure the current. Now, we can see that the relationship in here, that they are very nonlinear. That's why the battery is, why sometimes how to correctly estimate the state of charge is challenging. So this often the state of charge and open voltage, open circuit voltage is nonlinear. It depends on what type of battery we are talking about, the chemistry they use. So the shape may be different. And then also they will propose the hysteresis effect. When we charge and discharge, they have a different curve. And likewise, and the C rate means that how fast we charge the battery and or discharge the battery. So it means that how much power, like when we use the electric vehicle. So it all will affect the voltage level at different capacity. So this just shows some of the property between the terminal voltage and the capacity at different capacity under different charging and discharging rate. We can see that they are very, very nonlinear. And likewise, capacitor battery is also very sensitive to temperature. This shown about the capacity of the battery under different temperature conditions. And then also the internal resistance that is also very greatly with respect to different temperature or operating condition. So by and large, I show you all those nonlinear graph is to tell you that there's many factors that can affect the battery performance, and they are highly nonlinear, and that's why it is quite challenging to do state of charge and state of health and remaining useful life and also state of function estimation. So in our lab, we have been working on this problem since 2007. So we have developed something called state of co-estimation algorithm to handle all those issues. So the co-estimation algorithm is developed based on the electric circuit model that we have just described, and it can perform real-time state of charge and state of health estimation. And also the co-estimation algorithm has several features for accurate state of health estimation. So we have established something called a regional awareness adaptive parameter identification approach, an adaptive observer gain update method, and also we develop a state of charge state of health observer. So they are all those techniques has been reported in those publications and beyond. Most of the observer-based state of charge estimation algorithm proposed so far design the state observer based on a model with fixed parameters and which are obtained from offline identification. However, we just say that all the parameters are subject to change and needed to be identified with a proper frequency during the state of charge estimation, because we have just shown in the previous several slides that all the nonlinearity and then the value is really dependent on like a operating temperature and charging or discharging rate, so on and so forth. So therefore, we want to identify the parameter of the battery online. The adaptive battery parameter state of charge co-estimation approach was proposed since the battery parameters are function of the state of charge, C rate, temperature, and aging. So in here, that is some of the technique. We have used the adaptive parameter identification by measuring the current and voltage based on the circuit model. So we will then use those that identify the R0, R1, C1, RC1, so on and so forth of the mathematical model in real time. So or at that specific operating condition, and then we feed the information and then develop a observer to observe what's the state of the state of charge of the and state of health of the battery. So a little bit more details is that that is what we have done. We have like using a moving window least square feet, battery parameter estimate all the parameter, and design the observer gain. So that is the model we use. In this application, we use one RC model, and then the reason is that we are working on the electric vehicle applications. So based on these state-space models that we describe, this state-space model is basically describe these circuits. So, and all those details has been reported in this paper. Then we apply our technique, and then on with one of our project on the electric vehicle. So the industrial partner at that time is a Huawei, and then we test the battery under different temperature conditions using the pulse discharge method. The co-estimation algorithm was tested on the data compared with other algorithms, including Kalman filter and Coulomb counting. Now, Coulomb counting is usually the gold standard for people use, but there's several drawback of Coulomb counting, like we need to know exactly the initial state, so on and so forth. So we find, so those is the state of charge estimation error, and then that's a green line is the Coulomb counting, blue line is the Kalman filter, and then the red line is the co-estimation algorithm that we use. So usually the industry say that if your state of charge is bounded within like 5%, then they are good enough. So this is a corresponding state of charge errors. Then we can see that our system is in here, is unbiased. Red, of course, 0 is the best. So that is a histogram of the state of charge estimates when we comparing with these three approaches. This is under all those different temperature conditions. And also, we would like to make sure that, what's the time now? Okay. So we also apply it on the stationary batteries on the microgrid. So to showcase how this state of charge, the co-estimation algorithm is doing in terms of state of function. So we have developed a called smart battery gauge. It's basically a microcontroller implement our co-estimation algorithm on it. So we use it to interpret the estimated state of charge and state of function into meaningful information. So in here, we use the EV as an example. In this application, with the state smart battery gauge, we use an AI approach to predict the state of function of the battery. In this particular problem is that we are working with the Samsung. So to estimate the remaining driving range of the electric vehicle through analyzing the state of charge, state of health of the battery, and the traffic and the weather. So after the drivers set a destination, and then we will base on the big data, and then including the route they take, like from Google Map, and then the real-time traffic condition from Google Map, and then the weather data from the weather forecasting station, and the historical driving data is that how the driver drive his vehicle, which is very important. And then we fit all those data into the ANFIS, and then to predict how much the route and then the energy required. And then we have also a simulator that is very commonly used in the transportation system, say that based on the drivers, that the car, and then at that time the sunshine, and then they can estimate the energy they use. So the missing part is what is the state of charge and state of health of the battery at the time the user want to do the trip and then on the road. So that is where the state of charge and state of health estimations will do in real time to do this calculation. So all those work has been reported in the estimation, and then we have several patents on this work also. So with all those information acquired, then this smart battery gauge will interpret them into meaningful information such as the remaining driving range, the predicted time of arrival, and whether the vehicle can arrive in the destination. So we can see that through the time and distance, and then the actual speed and then the predicted speed, and then also what is the actual stage of charge of the battery as a function of time, which means that how they drive, and then our estimated state of charge. They are very, very accurate. So if the state of charge of the battery is estimated accurately, the remaining driving range will be predicted accurately. Otherwise, the remaining driving range will be predicted wrong, and then can be result in potential finance and time loss. So that is the range estimation cost function. So if there's zero error, then everything is great. And then if have positive error, then the penalty will go exponentially high. But if have negative error, then which is good, as there's not much issue. So that is how we use the state of functions for the applications we are dealing with. And also another application we have used the smart battery gauge is being used is in the microgrid. So we have used this, developed something called Ramus hardware in the loop testbed. What basically is a microgrid simulator with actual battery, which is shown here. The battery pack contains 12 Samsung lithium-ion batteries. And in here, so this is all the battery. Then the results show that proposed method can accurately estimate the state of charge of each cell and also the battery pack with 0.6% mean absolute state of charge estimation error and 2.3% maximum absolute state of charge estimation error. So this, again, the result fulfill most of the industry requirement. We have, this is a smart battery gauge. So where we have implemented the co-estimation algorithm on it. So this slide shows the Butler Farm microgrid at North Carolina Electric Member Cooperative. So they are actually using our equipment already. So our SPG only require 2 connections, 1 power cord and 1 Ethernet cable for communicating with the battery management system of the battery bank. And usually the battery bank costs around $1 million per bank. And then we have also worked with Duke Energy, and then they also implement our smart battery gauge with the SAF lithium-ion battery. So that is where it is, and when there's our team, and then with the Duke Energy teams, and we implement them. So there's me, and then there's 3 other PhD students. At that time, we work together. This is the related publications of our work in the smart battery gauge and application to the microgrid and co-estimation algorithm. And then this is some of the conference proceeding, and then those are the related pattern. I know that my time is up, so I want to acknowledge all the students that has been working with me in the last 10 years on the smart battery gauge and also on the CODEM, is the Collaborative Distributed Energy and Management System in Microgrid. And then the following are the current students that I'm working with in our lab. And also I would like to acknowledge all those company and funding agents has been sponsoring our research, and some of our academia partners that we have been working with. And thank you very much of your attention, and may I answer any questions? I will be happy to.
Thank you very much, Dr. Shaw. Thank you for this nice presentation. Yes, I think the floor is open to questions, but before starting, when you explain this gauge and when you test it, we test it only on the what we call lithium battery. I'm wrong, or yes, it's the lithium.
Yes,
so,
we have. Correct. We have been focusing on the lithium-ion battery because that is the most popular battery. However, for the co-estimation algorithm, it will work with any type of battery that has like the structure of the battery is similar. For example, it can work with a lead acid battery. So yeah, so as long as the battery, the chemistry has similar type of dynamics, then we can apply the co-estimation on it.
Okay, so Doctor, anybody can ask a question. The floor is open. We thanks too much thanks too much LIU student branch for this nice preparation for this webinar. I think we have our colleague and he is a member of the committee in IES, Dr. Hadi. He raised his hand. Dr. Hadi can start if you want to ask a question.
Hi, Professor Cho, how are you?
Good, how about you?
Fine. I don't remember what was the last conference where we could meet.
It's
The COVID situation. Thank you very much for your excellent presentation, and I want to thank also the joint chapter, the joint chapter who organized this event along with the LIU student branch. Thanks for Dr. Abdullah, Dr. Arnaout for this. I have, in fact, three questions regarding some points. When you talk about co-estimation, you mentioned that you are estimating at the same time the state of the batteries along with the parameters. And you said that the parameters are nonlinear. I didn't quite understand what you mean by nonlinear. Are they non-constant parameters? Are they a function of other variables?
Yeah. Let me try to. Please say one more time, Hadid.
Yeah. Can I repeat? Okay. When you talk about co-estimation.
Yes.
Yeah. You mentioned that you are estimating at the same time the state of charge of the battery along with its parameters.
Yes.
And when you said that the parameters are nonlinear, what do you mean by that? Are they non-constant parameters? Are they a function of other variables?
Excellent question. Now we can see that. Let me see. Can you see the screen?
Not yet.
Oh, let me see. Maybe I'm. Here. Oh, maybe I unshare. Okay. Can you see the screen?
Yes.
Okay. So we can see that at different operating condition, the parameter will be different. Just like in here, the parameter will be different depends on where we are. So what the co-estimation algorithm is that we use the parameter estimation technique, which is quite used often, like in adaptive control or in the signal processing. So in real time, so we base on the input output mapping, based on the IL and VT that we are measuring, like every 1 minute, every 1 minute or every 15 seconds. So and then we use the model, which is this model. So the parameter will change, but usually for the battery, the time dynamics is quite slow unless it will start to catch fire. But otherwise, the dynamics is in terms of like hour. So or in terms of tens of minutes and hours. So we can sample in every 15 seconds. Then we get data to adapt to estimate the parameter, and then we use the parameter, and then feed it into the feed into the observer. Now, so this observer rely on the parameters, and then also the parameter rely on the output of the state of charge, because state of charge is one of the operating point. So they do it in real time. So what you are saying is yes, exactly correct. So this you handle all those nonlinearity issue in the battery.
Okay, thank you. Do I have time for two more questions, or Dr. Abdullah?
Yes, yes, you can have one
Okay.
extra question, no problem,
Okay.
colleague.
Thank you. Thank you. Dr. Shaw, you have mentioned the neural network. You have used neural network to
Yes.
as estimation technique. What learning technique have you used? Are you using online learning or offline learning? Are the data are changing or they are the same?
This is an excellent question. Now, for this particular application, is offline. Now, right now we are working on different AI technique for the online learning for battery dynamics. But if we focus on this one, we use offline. The reason is that there's a lot of data, so we need to predict how the user will drive his car, and then based on how the weather will affect the car. So this is all offline training.
Okay. And the learning time, it took how much time it took you to for the conversions of the algorithm?
Oh, I do not remember because the student did the work. But we use ENFIS, so ENFIS usually quite easy to train because we come up with the several rules, fuzzy rule, and then if they are well constructed, then really is learning a linear mapping. So probably hours. I just a wild guess. It will not be like a days and weeks. It's hours.
Okay. Okay. Thank you, Professor. Thank you.
Thank you, Hadi. Thank you very much. I think Danielle has a question. Danielle?
Yes, Dr. Chow, excellent presentation, very clear and understandable, and I love the references at the bottom. The question I have for you is the co-estimation works on a per cell basis. The cells are composed into modules and modules become a battery pack. How do you reconcile a large number of cells or modules into a coherent presentation, or because there are all sorts of ways where a particular module or even a cell can bring down a battery pack, which would be a severe change, for example, in its state of health, even if it's only happening in one cell. How do you reconcile all that sort of massive information or massive vulnerability into one number?
Yeah, you have asked an excellent question. In most of the research work previously done in the battery are on the cell level, and then in the one of my PhD students graduated a couple of years ago. Now is assistant professor in Taiwan. He has been working on the module level and pack level. So exactly what you have just asked, how we can use the cell level informations and then aggregate them to do a state of charge prediction for the module level and pack level. So there's a different technique. But my own thought is that I have also talked with the industry on this issue. Right now, for most of the in a battery bank that used in the stationary storage, they easily have thousands to tens of thousands cell. But for the BMS, they are basically monitored. It depends on this. They call it in parallel or in a series, and also in the hybrid mode. The way the cells are connected, they are able to monitor all those voltage on individual cell, and also they can also monitor the current. It seems that. So now the challenge is the temperature. So I don't have a good answer, but we are working on it because the temperature usually is the main killer. But we hope that we can, based on the current measurement, and then to catch it. I think right now with all those computational power, really manage like thousands of cells, just like a SCADA system on top of it will not be will be doable. So that's how I feel. But this is a question I hope that we can find a solution soon. Yeah, thank you.
Thank you.
Any other questions?
Yes, Dr. Chow, thank you for this amazing presentation. I have a question. Lithium-ion battery are known to overheat, especially in extreme temperatures like the Middle East. How can we solve this problem?
Yeah, you haven't thought about that. Yeah, you're right. Right now, lithium-ion battery, the temperature is the main issue, as the question asked last time. That I doubt that the system can. So we still cannot monitor the temperature of every single cell, but like I put like a 6 thermocouple in a pack as an average temperature. But I think most of the lithium-ion battery, like in the vehicle, in the EV, and also in the stationary battery, they put it into a air-conditioned room. So the temperature management of the HVAC of the pack level or in the room, they are well regulated, like I say, to 20 or 25 degrees C. But if we do not regulate it, and also so to me, in the EV application, in the microgrid applications, then they have an external HVAC system to regulate the operating temperature. But if you don't have the operating temperature, and I believe for the lithium-ion battery, they have a different type of chemistry, like a lithium phosphide, lithium magnesium. Hopefully, maybe some of the chemistry are more resilient to high temperature. You may consider to talk to the vendor. Maybe some of the lithium.
So we need a separate air conditioning system for when we talk about EVs or phones or something like that. But when it comes to huge mechanisms like factories and such things, it is never used, or it's not ideal to be used.
I think for the factory, I thought that the battery should be under are they the temperature, the environment control the temperature. If not, what I would suggest is that I think some of lithium, because the problem of the temperature of lithium-ion is not really the operating temperature, but it's the runaway temperature. Is that when there's a short circuit inside the battery, like for example, the separator is broken because of the dendrites started to grow and then create a short circuit. So, and then the I square out, the I go to infinity. So to burn the lithium-ion battery. So I think the question you're asking is more tied with the specific temperature range of the lithium-ion battery. So I believe there's some lithium-ion battery that probably are designed for high temperature. But that's I guess.
Yeah. Yes. Thank you.
Yeah, you're welcome.
Thank you, Professor Shou, for this nice presentation. In fact, I have, if it's possible, 2 questions. The first one is related to the the chemistry of the battery. As you know, and as I know, there is different type of lithium-ion batteries, LCF, LCO, like LiO4, and so on. So this technique that you used is so it's applicable for all these type of battery. There is a specific, if we want to have a comparison across all type. So did you find any advantage for any type of battery regarding the other, or all lithium batteries has the same behavior?
Yeah, this is also a very excellent question. No, the lithium-ion battery, they don't have different chemistry. They will have a different type of behavior. For example, if I go to the in here. So I think the sum of the battery, the VOC SOC curve is like this. It's very flat in the middle. So this is good for application perspective. And because over a wide range of the state of charge operating condition, and then the voltage remain the same. However, that is not good for the like a co-estimation algorithm, and because there's not much change. So many people now also we use is that once we hit that region, then from a control perspective, a control theory perspective, it means that the observability matrix, once it goes into a very flat region, then the controllability matrix become the matrix start to have the rank is low and or ill conditioned. So usually that cause a much larger estimation error. Usually we use a hybrid mode. So once we have an accurate estimation of the initial the state estimation, then once we hit this region, then we will use the Coulomb counting, which is much less sensitive to this type of characteristic of the lithium-ion battery. So, and also for some of the lithium-ion battery, it's just like this, and has a lot of changes of the VOC-SOC curve. In that case, then we use all those co-estimation algorithms. Then the observability matrix, the rank is a full rank and then well conditioned, and the accuracy is very accurate. So in short is that the lithium-ion battery, typically the structure can be described by this model, but also some of the detail like a VOC-SOC curve, which is very important, like how it looks like will affect the overall performance of the estimation. So different technique has different advantage and disadvantage. Like Coulomb counting, if we miss the initial guess of condition is wrong, then we have a lot of accumulation error of use Coulomb counting. But if we don't, then Coulomb counting is really good.
Okay, thank you. The second question is regarding the hysteresis effect. In fact, the area of this hysteresis is depend on what? If we have a large area or a small area?
Oh, that depends on many factors. This is great question. Now it depends on the aging. When the battery start to age, then the gap is larger and larger. And also it depends on the chemistry. So quite often then we of course hope that the battery is the hysteresis effect, the less the better. But by and large is that the aging will cause a larger and larger hysteresis gap. Aging.
Okay, thanks a lot, Doctor.
Thank you very much. I just saw Professor Walid Kamal is with us. He's in Canada. He was the, if you want, the previous chair of this joint chapter. Thank you, Walid. Hope to see you in Lebanon. Okay, so we ask you all, please, if you can turn your camera. We would like to take a picture. Walid, you look good, by the way. Yeah? You look very good. Dr. Shu, can you stop sharing because we can get more people on the screen?
I see. Okay.
Ernest here again. Okay, thank you, Ernest, our colleague from American University of Beirut. And for sure, Muhammad, thank you very much. Thank you for everybody for attending. Please, LIU student, can you take the picture? And I will take some snapshot in the same time. Thank you very much. Thank you.
Yes, we already did.
Okay. Thank you very much, friend.
Thank you, Dr. Abdullah.
Thank you again, and thank you for your time, Professor Shu. and hope to see you next time in Lebanon face to face with